Okay, welcome back, class. Good to be with you. It's Whitlock and Schluter Chapter 7. We're going to focus on the binomial distribution for this component right here. And to get into it, I want to just point out that we've seen a number of different probability distributions. We looked at the mound, special case of which is the bell. Okay, that's sort of a default type of situation. There's the rectangle, like the die, or the raffle, drawing from a hat, or what have you. Then there's also the skewed type of distributions. We'll talk about skewed right. I could flip that and do a skew left. Now, the binomial is a very particular distribution. It comes from a certain set of assumptions, which we'll discuss momentarily. It's discrete, first of all, so you don't have the continuous line. It always is going to be given just by a histogram. Okay, so let's histogram up here. And that's the idea, but I want to class that in along with all of these other distributions. Okay, it's a very particular one. And we'll just jump over to some RStudio and look at a specific case. We'll do the one from the book, and I'm just going to define a variable called out. dbinom is the R command that we want to use, and I'm just going to kind of model how it goes. We're going to use 0 through 27 because we had these 27 flowers. So size 27, probability. The probability of the event with the flowers was 0.25. So that's going to be my out, and then we'll do a bar plot. Let's plot those values that came out. Those are the binomial probabilities with 0 to 27. And this is what results. You can see it's roughly mound-shaped. However, I want to point out it actually has probability on all of those values on the right. I could show that by a C-bind. That's column bind. 0 to 27 with out. And those are the values. So you can see here, at number 10, that's 0.06. So 10's 0.06, still a 6% probability. By 14, we're at 0.005, or excuse me, 13, we're at 0.005. Not too much going on there, and then it just gets really tiny as we go out. Property of this guy, let's pull up the out again. Let's not do 0.25, let's do 0.75. And then we'll run his bar plot. Look at that. Mirror image. So it did a mirror image. If you were to change the value, let's say to 0.9, it's going to make it more extreme. Okay. If I were to change it to 0.5, it'll make it perfectly symmetric. Right in the middle. So that's how the behavior goes. It goes according to the proportion of the number of successes. So what is the thing? Okay, the binomial probability distribution is defined as this guy right here. Well, okay, it's coming down here. It's the number of successes in n independent, identical success-fail trials. Okay, so a trial is a single case. That would be the single flower that has a 25% chance of success or not. Okay, that's always going to happen. You get 27 of those, and then you count up how many successes did I get. Each flower is independent. We're assuming the number of flowers that had success, that is the value of the binomial random variable. So it has those three components. We have number of successes, whether they're independent, they must be, and let's see, they're all identical. Okay, identical being each single flower has the same success fail probabilities. Okay, so that covers, yes, there they are right there. Okay, got it. Now, for notation, I'm going to use this. X follows a binomial probability distribution with parameters n and p. Okay, so this notation here, we'll use it later, but follows some distribution. N is called the size, and then P is the probability of success. So that's P of S, where S is success. Or you can say probability of success, where success is very arbitrary. Okay, let's do a very simple example here. And we'll just talk about my wife. Let's say that she has 3 babies, 2 girls. All right, now I have 2 daughters. In fact, that's all I have. So we're just doing a hypothetical here. Okay, and let's just consider on the first baby. First baby, we're going to let probability of success be having a girl. Again, that's totally arbitrary, but we'll do it that way. And we'll say it's 50%. It's not exactly 50%, it's closer to 51%, but we'll just do this for the sake of discussion. Okay, so 50% there. Probability of the boy, of course, is going to be 1 minus, that's 50%. If I draw the histogram of that, then if we have 0 girls, which is the same as 1 boy, that's 50%. Or if we have 1 girl, then that's 50%. Okay, so we got that one there. Now let's jump up to the n equals 2 case. We write it like x follows a binomial probability distribution with n equals 2 and p equals 0.5. So what's the probability of 2 girls? Not so easy. Okay. Well, excuse me, it's not so easy to get the whole distribution, which is going to be like this: 0, 1, or 2. Those are all the possible cases. Okay. Well, the 2 girls case, that is actually easy. It's success and success. So when I say that, I'm thinking probability of S and S. Therefore, we multiply the 2 probabilities. Half by a half is a quarter. Okay, so we've got our quarter. Awesome. So that's 1/4. Now, let's jump down to the 0 girls. That one's going to be fail, fail. Pretty much the same as the success, success. So we go here. The 1 girl case, there's a little wrinkle, because I could get girl, boy, or boy, girl. And so that's going to give me quarter for girl first, quarter for girl second, half total. So the probability goes like this, and that's a half. So that's my probability distribution for the n equals 2 case. This was the n equals 1 case. Awesome. Now, let's go to the n equals 3 case. Okay, so x follows a binomial probability distribution with n equals 3, p equals 0.5. Probability of 3 girls is, and we can see success and success and success. So that's 1/2 by 1/2 by 1/2 equals 1/8. At this point in time, you might be thinking to yourself, oh my goodness, is he actually going to say all that stuff? No, I think that would be deadpan boring. So I'm not going to do all that. It's easier to probably read it. So we get 1/8 there. When you go and look at the 1/3, wow. I'm sorry, the case of 3, it's going to be boy, 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 same 1/8. When you go to the 2 girl case, check it out. We're going to wind up with 3/8. Please confirm. 1 girl case is symmetric to it, 3/8. And so this is what the distribution looks like. You can see again it's perfectly symmetric, just as the other 2 were. And the cool thing is that scales up to any size n. It's awesome. Now, we can go beyond that then and construct a general formula for the binomial probability distribution. Very cool. Okay, so let's go ahead and do that. I've got a little background stuff here. Go ahead and take a look. And the way I'd like to get at it is to just go right into this table. And this is the general table for the, that really would best be put n equals 3 case. Okay, so 3 girls, x equals 3, was half times half times half. So that one's good to go. Now, the 3 boys case, or the 0 girls, is 1 minus p, which in our case was 1 minus half. So 1 minus half, 1 minus half, 1 minus half. That also got us our 0 girls case. But for the 2 girls case, I had girl, girl, boy, but we could have girl, boy, girl, or boy, girl, girl. Notice that this one here is p cubed, where p is the probability of success. And this one here was 1 minus p all cubed. 1 minus p is the probability of failure. These 3, if I notice their similarities, they're all p squared times 1 minus p. And if you will, I'm going to put that to the power 1. By contrast, the cases where I only have 1 girl, there are 3 of them, they all have a single p, so I get p to the 1 power, and 1 minus p. There's 2 of those in each one, so that's to the 2nd power. And if I just get a little creative, I'm going to go ahead and put 1 minus p here, and that's to the 0 power, because anything raised to the 0 power is just 1. So that works fine. And similarly, I want to go ahead and just put a p to the 0 power here. Well, now things are lining up for me. I notice that this exponent right here is exactly the value of x that I'm interested in. Notice my x. And then this exponent right here, it's not x, but it's related to x. It turns out to be n minus x. We're starting off with n equals 3. And what that gives me then is the general structure of the probability values for this binomial probability distribution. That's got it. Now, what do I lack? Well, I lack the count of how many cases there are. There was 1 case here. It turned out that there were, let's put it here. There's 1 case here, there were 3 here, there were 3 here, there's 1 there. So how do we get that? Well, I'm not going to go into detail on it in the interest of time, but it turns out that there's a formula called combinations, and the combination is the answer. It is the number of ways to pick x out of n items. And for my math majors, you may have seen that written as NCX. You may have seen it as n comma x here. Okay. But it all is this formula. And for my non-math majors, I want to note the exclamation mark is a technical term called factorial. And for example, if you have 5 factorial, it just means you take 5 times 4 times 3 times 2 times 1, which is 120. And we have the designation 1 factorial equals 1, and we're going to let 0 factorial also equal 1. Okay, this is the general definition of it. And so when we combine everything together, our result is n factorial. So the probability that x is some particular value is n factorial over x factorial times n minus x factorial times p to the x times 1 minus p raised to the n minus x. Okay, we've got some R commands to actually run that, which we did at the beginning, and that gives us a good time segment, so we'll go ahead and pause there, and we'll do examples in the next one.